Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. Bam! So we are continuing on with our titration example number 1. And today we are going to finish this up. And we're going to do the most complicated one here of them all, and that is the equivalence point calculation. So let's do the equivalence point calculation. So we're going to calculate the moles of acid. And that is using the volume and the molarity. So that's 100 milliliters. Now I've converted those milliliters into liters with that second unit conversion. The third unit conversion here is the molarity. And the molarity is 0.025 molar, which is moles per liter. You should see that the milliliters cancels out, the liters cancels out, and you're left with moles. And this is the moles of the benzoic acid. So you have 0.0025 moles of benzoic acid. Now, since we are at the equivalence point, there's something very important that occurs at the equivalence point, and we're going to calculate the moles of base. Now, knowing that we're at the equivalence point, we have the moles of the acid is equal to the moles of the base. This dictates what we do in this problem mathematically. So therefore, if we have 0.0025 moles of benzoic acid, 0.0025 moles of sodium hydroxide is required to reach the equivalence point. All right, so now we have the known amount of moles of the strong base, that's sodium hydroxide. So now we're going to calculate the volume of base required or necessary at the equivalence point. So we have the moles, we had the molarity. So we have the moles of the base, and we had the molarity, which was 0.100 moles per liter. So I've, flipped that so that the units cancel out. That is, the moles cancel out. Then I'm going to convert this into milliliters, so that's why we're multiplying this by 1,000. And we get 25 milliliters of sodium hydroxide. So 25 milliliters of sodium hydroxide is required at the equivalence point. Okay, all right. Now what we're going to do is we're going to calculate the total volume at the equivalence point. Now we started off with 100 mils of the benzoic acid, and we had used 25 milliliters of the sodium hydroxide. So we're going to add these two numbers up, and we get 125 milliliters for the total final volume at the equivalence point, that is. Okay, we're going to calculate the concentration of the conjugate base. That is, the acid reacts with the base, that's the sodium hydroxide, and the acid is completely, the benzoic acid, the acid is completely converted to its conjugate base, the benzoate ion. Okay, and this is in a new volume, and so this is at the equivalence point, so now we need to calculate that concentration of the conjugate of the acid. Okay, so the conjugate of the acid, that is benzoate ion, is the moles of benzoate divided by the total volume. Okay, the total volume is in liters because I want a molarity. And so this is the value that I get, and that is 0.020 molar of the benzoate ion. So let me repeat this because this is the most important part, and this seems to be a confusing part. When we have our acid and it reacts with our base, all that acid is now converted into its conjugate. Now that conjugate is the same number of moles that we had previously of the acid. And now this conjugate is in a new volume because we added sodium hydroxide to reach this equivalence point. So therefore the moles is the same of the benzoic acid and its conjugate, benzoate ion. That's why the mole value is the same. And the total volume is what's necessary so that we get the concentration of the benzoate ion at the equivalence point. All right, we're going to be using this value here. So at the equivalence point, all the acid has been converted to its conjugate. Therefore, a new equation must be written, and the appropriate K for that equation must be written as well. Starting with the conjugate to the acid, that is the conjugate base, for the next ice table. So we're going to go to the next slide with that next ice table. Okay, all right, so we're going to write that equation again. So this is the benzoate ion plus water. Remember, we're always adding water. Okay, and we're going to get the benzoic acid and the hydroxide ion on the product side. These are the two conjugates to the reactants. Okay, that is plus or minus a hydrogen. We're going to do an ice table, that is initial change in equilibrium. We just calculated the concentration of the benzoate ion at the equivalence point. That is this value of 0.020 molar. The concentration of the water, well, that's a liquid, so I'm going to ignore that. The concentration of the benzoic acid and the hydroxide. Now remember, this is a brand new ice table at the equivalence point. So all the benzoic acid has been consumed. There is no benzoic acid, so I need to figure out how much is going to be formed based on this equilibrium problem. So this is going to be a 0 and a 0 for the products, just like any equilibrium reaction. Now the change is that this is going to shift to the right. That means it's going to shift to products. That means that the reactants are going to decrease, the products are going to increase. And we're going to use stoichiometric coefficients. Okay, so we have a negative x, that's a minus x, nothing for the water, a plus x and a plus x for both the products. We're going to add up the initial and the change to equal our equilibrium. That's 0.020 minus x for the benzoate ion, nothing for the water. Benzoic acid is just an x, and the hydroxide is just an x. Okay, all right. Now what we need to do is we need to write the KB for this equation. Now I want you to understand this is the KB. There's a switch of the equation. There's a switch of the K. Why is it a KB? Because on the product side I have a hydroxide. And I cannot write a Ka because that would be a hydronium ion. Since I have a hydroxide, I'm doing a Kb. That's a constant for the base. So I got my two products is equal to my Kb. So Kb is equal to benzoic acid times hydroxide in the numerator, and the benzoate ion is in the denominator. I'm going to use my equilibrium stuff to get my Kb value. So I got my Kw is equal to Ka times Kb. I got 1 times 10 to the negative 14 for the constant for water. That's the Kw is equal to the Ka that was given to me in this problem. That's 6.25 times 10 to the negative 5. I'm going to divide both sides by that Ka value to get the Kb. This Kb is going to go right into my Kb expression right there. Okay, all right, now I'm going to put in these equilibrium values right into that Kb expression, and let's see what pops out of that. So I got my Kb, which is 1.6 times 10 to the negative 10. Remember, that times 10 to the negative 10, that's telling you that this is a very, very weak base. Okay, my x squared term is in the numerator, and that is the benzoic acid times the hydroxide of the equilibrium x times x. And then in my denominator, I have 0.020 minus x. So I'm going to ask myself this question, as I always ask it when doing this. If 100 times the K, if that is less than the initial concentration, then I'm going to use the approximation and not the quadratic equation. So that is 1.6 times 10 to the negative 10, that's the Kb, times 100. Is that less than 0.020? If that is true, of which it is in this case, then I'm going to get rid of the minus x. And so now I'm going to take 1.6 times 10 to the negative 10, multiply that by 0.020, take the square root of that, solving for x, and this is my x value at 1.8 times 10 to the negative 6. Now I'm going to look back in my ice table and find out what is x equal to. X is equal to the benzoic acid concentration. X is equal to the hydroxide ion concentration. I'm trying to solve for the pH. So I'm going to say X is equal to the hydroxide, which is the hydroxide ion concentration is 1.8 times 10 to the negative 6 molar. Okay, now I need to solve for the pH. There's a variety of different ways of doing this, but I'm going to use one particular way here, and I'm going to use the Kw is equal to hydroxide times hydronium ion concentration. We know the Kw. We just used that earlier in this problem here. That's 1.0 times 10 to the negative 14. I'm going to plug in the hydroxide here where it belongs, and I'm going to solve for the hydronium ion concentration. The hydronium ion concentration that I just acquired was 5.6 times 10 to the negative 9 molar. Now I'm going to solve for the pH, so I'm going to take the negative log of that same value to get the pH, and my pH is equal to 8.25. Notice I got 2 decimal places with every single pH or pH value. Okay, so the pH is 8.25. Now, does this value make sense? So we are at the equivalence point. We are titrating a weak acid with a strong base. The moles of the acid equal the moles of the base at the equivalence point. And since the strong base is a strong base, and therefore the pH will be greater than 7. And so this value makes sense. So yes, it is certainly basic, as one would predict, and hopefully we did that with the graph at the very beginning of this titration problem here. It's certainly not 7, okay? You would get a pH of 7 if, and only if, you mixed a strong acid and a strong base together. Equal volumes, equal concentrations, or just a strong acid and a strong base. You're going to get a pH value of 7. So that's what you would get. But this is a weak and a strong, and those are most certainly different, and that's why these are more complicated problems. Okay, so which is the best indicator to use for the titration? Now recall that we had a certain pH that was at the equivalence point. So the indicator is dependent upon what the pH is at the equivalence point. Since the pH equals 8.25 at the equivalence point, or the end point, one should choose an indicator in which the changes of color occur at or around this same pH of 8.25. So, or if one knows the pKa values of the indicators, one would choose an indicator where the pKa matches the pH at the equivalence point, or as close as possible. So, upon analyzing the prior chart of this particular problem, phenolphthalein would be the best indicator, as it changes from colorless in an acidic solution to pink or fuchsia when it's above a pH of 8. Okay? So I want to give you an equivalence point understanding and an analogy here. I'm going to give you two of them so that you do understand what's happening at the equivalence point, because this is the most complicated problem here, okay, of a titration problem. So the chemical equation prior to the addition of the titrant, that is the sodium hydroxide in this particular case, was benzoic acid plus water gives the benzoate ion and the hydronium ion. That's like the equation prior to the addition of the sodium hydroxide. It's also the same equation at the halfway or the midway point. Okay, with the addition of base, that's sodium hydroxide, to the acid, this is what occurs. So I want you to understand that sodium hydroxide is a strong base, so therefore it dissociates 100%. The sodium ion does not contribute to the pH either in an acidic or basic way because it's a conjugate to a strong. It is 100% disassociated. So therefore, what's important is the hydroxide ion. And what does the hydroxide ion interact with? Hydroxide is a base, it will react with the acid. So I got the benzoic acid plus the hydroxide ion from sodium hydroxide produces benzoate ion and water. And I've highlighted here for you the hydrogen and the hydroxide. Those two combine to form the HOH or H2O. Okay, and then what remains after the hydroxide reacts with the acid and removes the hydrogen to form water, what remains of the benzoic acid is the benzoate ion, and that's what is formed on the product side. Okay, so therefore, with the addition of more and more base, the acid decreases, the benzoic acid that is, decreases, and the conjugate of the acid, in this case the benzoate ion, that is the conjugate base, increases in the same proportion as the amount of base added, of the strong base that is. Okay, this will occur until all the acid is converted to the conjugate base. This is the equivalence point, i.e. the point in which the moles of the acid originally present are equal to the moles of the strong base that is added in this particular case. At this point, there are no more moles of acid remaining since all the acid has been consumed by the base. But the conjugate base that is formed is equal to the number of moles of acid originally present. However, a new volume must be required since the strong base has been added, which increases the volume. This is why there is an equation switch at the equivalence point and a corresponding change in the K value. So this is the equation switch. So I have benzoate ion plus water gives benzoic acid and the hydroxide. This is how I'm coming up with the equivalence point calculation for the equation switch right there. Okay, now an analogy to represent this. Okay, so hydronium ion Ka, hydroxide ion Kb. Make sure you understand that too. That's very important. Hydronium ion Ka, because that's an acid. Hydroxide ion is a Kb because it's a base. So, an analogy. I've got some bottles of water. Pretend this is our benzoic acid in this particular case. We got an equilibrium and we got a conjugate base to that acid. Notice that all these bottles, all the lids have been taken off. What are the lids? The lids are the hydrogen ions that have been removed from the acid itself. Okay, another analogy. Okay, this is the acid. This is a classroom filled with chemistry students. I got an equilibrium reaction. The conjugate base of that acid is the removal of all those students. Where did all those students go? Well, they are at the game, and they are at the football game. That is the soccer game. Okay, those are the ions that have been removed. And of course, go Aggies, UC Davis, go, go, go. Okay, so in other words, if you have 5 moles of acid, and it reacts with 5 moles of base, and this is at the equivalence point, then there are 5 moles of conjugate base that is formed at the equivalence point. Okay, so hopefully those 2 different analogies works well for you. Hopefully you understand that. This equivalence point calculation is critical. You got 3 very important calculations. One is before adding the strong, that is before titration. One is at the halfway or midway point, and one is the equivalence point calculation. Those are our 3 central points of pH calculation. Okay, I am the Crazy Hat Chemist, and I'm not quite done because I got a crazy hat. I've been wearing this hat for this entire problem of a titration problem number 1. Okay, remember, you can donate to my website because it takes a lot of time to make these videos. You can get a sticker if you want, put that on your hydro flask or your computer, maybe even get a t-shirt. Super cool. You got to get both or one. All right, give me a thumbs up if you feel like that video, subscribe to my YouTube channel, pass it on to all your cool chemistry friends, get a sticker. Talk to you later. Bye for now.